In this, the 22nd lecture of Symmetries, Particles and Fields, we're going to define a new kind of representation called the Induced Representation, and then apply it to irreducible representations of the Poincare group. Just before we start that, I noticed that I'd implicitly assumed Hermitian operators in the previous lecture when I said that the eigenvalue of this big operator p mu acting on a one particle state gives us back little p mu. So this is for Hermitian p, big P mu hat. We've mainly been working in the anti-Hermitian Lie algebra basis, and indeed we can have anti-Hermitian operators too. So the difference here is a minus sign because we get a factor of I times p mu as the eigenvalue for the anti-Hermitian operator. We'll see that this time. Okay, so irreducible representations of the Poincare group. So we've seen various fields during this course. So there's the scalar field, we've seen fermionic, spinor field, which will be used for fermions, and we've seen spin 1 gauge bosons. And we've discussed how these fields behave with respect to the internal symmetries, but what are these fields in terms of the external ones? So the question, what are they in terms of external symmetries? I'm having trouble with this app. And the answer, as we've been saying a few times, is that there are irreps of the Poincare group. So, okay, normally one looks for finite dimensional representations of the groups. And the Poincare group does have finite representations, finite dimensional representations. But the problem with these is that they're not unitary. And for our quantum states, we need unitary representations. So we require unitary and in fact irreducible reps for a quantum theory. So the Poincare group does have these, but they're infinite dimensional. They're induced representations of the Poincare group. And they act on the fields which are functions of Minkowski space. So we have this Minkowski space. It's really 1 plus 3, I guess. So the parameters that parameterize these, we might call x mu, for instance. And this Minkowski space manifold is defined to be the manifold, the Poincare group in a coset with the Lorenz group. So if you think about it, Poincare involves translations and Lorenz transformations, but we have an equivalence relation between all states just which are related by a Lorenz transformation. The theory is going to be Lorenz invariant, and so doing a Lorenz transformation won't change any of the physics at all. So, all right, let's apply, okay. So induced representation is a new term, and we need to give you first the general idea of induced representations, and then I'll apply it to the representations of a Poincare group. So let's do induced reps first. So consider the space of scalar functions. Scalar functions, let's call it phi of x, where x are now some coordinates on the group manifold. So these scalar functions defined on an orbit and this orbit's going to have a manifold which is G coset with H, where H is the little group at some base point. At some base point, X, let's call the coordinates of that base point collectively X0, and it's in this manifold. So we can define an infinite dimensional representation of G. So an infinite dimensional representation, big D we'll call it, of G, using the following. So big D of G acting on phi as a function of x is the same thing as phi at G to the -1 of x. So in other words, the transformed function at x has the value of the original function at the point mapped to x. Okay, so that's the definition of D. We must check that this is a group, so we have to check the group composition rule. So we know what that must be. We have this, we have to obtain this result. Sorry. Where's the eraser? All right, so if we apply the rule which is here twice in this, we have that the left-hand side is equal to d g2 phi evaluated at g1 to the minus 1 of x is equal to d. So then we apply the left-hand side. Sorry, we apply the equation above again, and we get d of g1, d of g2 phi on x, which is exactly the composition rule that we need. So note that the little group acts trivially at the point x0. So for some member h of the little group, dh phi acting at x0 is equal to phi of h to the minus 1 x0, and because this is h is the little group, h is in the little group, h to the minus 1 is also in the little group, and so this leaves x0 unchanged. And this is why we regard phi as a scalar function, essentially this last fact. All right, that's fine. So that's for a space of scalar functions. Let's generalize to a space of vector functions. We'll call these in general psi of x, and these take some values in a vector space. Call that vector space V. So it's necessary that there's a finite dimensional representation D of the little group acting on V. So now, now we've generalized to this space of vector functions. H acts non-trivially at the point x0. Unlike the case of the scalar function. So if I consider dh psi acting at x0, this is equal to d of h psi of x0. All right, so we define the full action of the group as d of g psi on psi at point x is equal to d of h of g of x acting on psi of g to the minus 1 of x. So this is the new ingredient, this h of g of x. What is it? That's the question. So this is, what is this? In fact, as we'll see, there's some freedom in fixing it. But anyway, let's just take this as given now and check the composition rule. And if you do that, it's a two-line bit of algebra to show that we must have some relations between these h's. And it's called the co-cycle condition. Which reads that h of g1, g2, comma x is h of g1, comma x, h of g2, g1 to the minus 1 at x. Okay, so we need some solution to this condition, and we solve it by choosing some element of G that smoothly maps x to x0. So a specific element of G, well, let's call it G0 of x. So G0 is the specific element that smoothly maps x to x0. So note that this exists if the action of the group is transitive. But it isn't unique because we can follow any G0 of x by an element of H. And the argument remains the same. So we put that G0 of x0 is the identity element. All right. So for any group element and any point on the group manifold, there are two roots from G to the minus 1 of x to x0. So for all G and x, there exist two roots from G to the minus 1 of x to x0. So one is by G0 of G to the minus 1 of x. And the other is G followed by G0 of x. And the difference between these two is some element of the little group, which turns out to be the function we want. So let's say that is the function h of g and x that we want. So h of g of x is the thing that solves the co-cycle condition, essentially. Now, if you substitute in the following, so if you substitute h of g of x equal to g0 of x, g0 of g to the minus 1 of x, so g0 to the minus 1, then you substitute that into the co-cycle condition, you'll see that it does indeed solve it. So the result is that big D is again a representation of the group. And it's called the representation of G induced from the representation D of the little group. Usually we in the applications that we're going to see anyway, D is an irreducible representation. All right. So to begin applying this for our one particle states, we have to go back to think about a unitary operator that's going to represent a Poincare transformation that's going to act on those quantum states. So let's introduce the unitary operator now. Is defined for a Poincare transformation. So U, remember so U is the unitary operator. It's going to represent the element lambda comma A of the Poincare, and this is defined to be the translation followed by, well, sorry, the Lorenz transformation followed by the translation. So this is the unitary operator corresponding to the Lorenz transformation. This one corresponding to the translation operator. So this is translation operator. And it's an abelian subgroup of the Poincare transformation. It's an abelian operator, essentially. And okay, so let's do it in 4 dimensions. So T of A is equal to e to the A mu P mu. So P mu here is an operator. We're going to put it to be anti-Hermitian. So note, okay, that's fine. All right, so the idea is that these operators act on states and give us back eigenvalues of the state. So you should notice that the Poincare element corresponding to this, well, this is just the product of 2, or the composition of 2 Poincare elements like that. But we can also write this as a different product. If you use the composition, the rule for the composition of Poincare operators, you'll see that that is true. And that means that when we represent this with the unitary operators, that on the left-hand side here, we would have the unitary operator corresponding to lambda. Here we would have T of A. So this is in the opposite ordering to the one that we had, that we defined before. And on the right-hand side, we have T of lambda A and U of lambda. Okay, so Irreducible representations of T are one-dimensional. And they're defined by a vector, which we're going to call little p, a ket with little p in it, such that, okay, so I'm going to now call the operator, I called it with hats before, but I'm going to omit the hat. So with a, but it's like a capital P with a stick, and I'm going to have so this is an anti-Hermitian operator. So we define that P mu acting on our state gives us back I P mu acting on the state. So this little P mu is the eigenvalue, and this big P is the operator, quantum operator. So what this means is that our translation operator acting on the state gives us e to the I a dot p times p. So the real vector, okay, so this, by this p I really mean the 4 vector p mu. So the real 4 vector p mu labels the representation. Okay, now if you check again the rules for composing elements of the Poincare group, you'll see the following. That if we multiply these 3 elements together, and you also have to know what the inverse is, which we defined before in the section 5. So I can compose these things on the right hand side, and we get lambda to the -1 and a, and this is equal to I and lambda a. If we use the rules. And so we represent this left hand side with operators. So we have a u lambda for this Lorenz transformation, and then we have with the operator p, we have e to the p dot a for the translation, and then we have a u of lambda to the -1 because u is unitary. Sorry, because it's just an inverse operator. And on the right hand side here, we just have a translation operator with lambda a instead of a. So this is p dot lambda a. Now, you can expand. This has got to be satisfied for arbitrary a mu. So you can expand to first order in a or to arbitrary order in a, in fact. And this implies that u of lambda times p mu u of lambda to the -1 is equal to p nu lambda nu mu. And this I'm going to call equation 9.1. Okay, so this implies that u of lambda to the -1 is times p mu times u of lambda to the -1 or to the -1 is equal to p nu lambda to the -1 nu mu, which in turn implies that if we consider p mu acting on some state, which is given by u of lambda acting on the p ket, okay, this is equal to, so we have to keep track of what's, you know, just a number and what is an operator here. So this is equal to u of lambda p nu lambda to the -1. So I'm using the above line acting on p. So here we've seeing that this is equal to u of lambda, of course, here. So all I've done is I've acted with the above equation on a ket p, little p, and acted on the left-hand side with u of lambda. So let's be clear, u is an operator, and so is p, and this is some number. It's really it's a matrix of numbers, really, given the nu. So this right-hand side now, so this operator just doesn't see the number and acts directly on the state to give us an extra factor of I p nu. So we see what this u of lambda operator does to the p mu operator. It gives us this it gives us a lambda to the -1. So in other words, a Lorenz transformation. So u of lambda acting on a set of states which are labeled by p generates a vector space V such that if we have p and p prime are in it, these are in it if they're related by a lambda to the -1, if they're related by a Lorenz transformation. In other words, p prime mu is equal to p lambda to the -1 of mu. So what this means is that their form momentum squared is identical. So the vector space consists of all states with the same form momentum squared, but otherwise connected by Lorenz transformation. And conversely, for any two states satisfying this, there is a Lorenz transformation linking them. So the physically relevant cases for us have p squared bigger than or equal to 0. So for a one particle state, for instance, that definitely have p squared bigger than or equal to 0. So we're going to restrict now to Lorenz transformations, proper orthochronous Lorenz transformations. So we have p0 is bigger than or equal to 0. So note, there's a continuum of these p mu's, and that's why the dimensionality of the irreducible representation is infinity. Okay, so we're going to finish there. Next time, we will carry on applying this and now construct our induced representation. The group is going to be the proper orthochronous Lorenz group in a semi-direct product with these four-dimensional translations. And we'll have to, our particular point for the induced representation will be a particular form momentum that depends if we've got a massive particle or not. If we've got a massive particle, you pick a form momentum which is at which the massive particle is at rest. So it turns out that that case is a bit simpler, and we'll do that one first, and then we'll move on to massless particles, which of course are traveling at the speed of light.